Alright, good morning. We are going to take a look at the pH calculation notes for those of you who were absent for these or just need a refresher. They are going to be dealing with pH, so we're still going to be using our pH equation, so negative log of the concentration of hydrogen ion. And we will also be taking a look at pOH during this, so same equation, just of our hydroxide ion concentration. So keep those in mind as we do these calculations. So it says at the top that Ka is called the acid dissociation constant. We have so far taken a look at equilibrium constants, and we've seen Kc and Kp. We talked about Kw, so the equilibrium constant for water. So when it just has the little a, that's just basically the equilibrium constant for acid, but they call it sometimes the acid dissociation constant because it's how acids break down. It gives us an idea of how much of the acid breaks down. If we have a high number, then that means our acid's pretty strong, it's going to break down. If we have a low number, then not much of it's going to break down, and we're going to have more of the reactant, and it's a weak acid. Excuse me. We also have Kb. It's called our base dissociation constant. So that is another term that's used. It's just for bases. Same concept though. These values are just like equilibrium constants and are determined by dividing the concentrations of the products of the reaction by the reactants. So products over reactants, same idea, same setup. When the hydrogen ion concentration at equilibrium, very important, the equilibrium part, is determined using something like an ice table or other methods, the pH can be calculated for the solution using our pH equation. When the hydroxide ion concentration at equilibrium is determined, the pOH can be determined using our equation, and then we can also find the pH from pOH. Remember that pH plus pOH is equal to 14. So we can go between those two values if we need to. The following are examples of the types of calculations that may be encountered. So we're going to take a look at some examples, how we work through these, and give you some tips along the way. So number one says to calculate the pH, so we're looking for pH, of a 0.45 molar solution of HCl. So the first thing we want to recognize in these questions is look at our chemical and decide is it an acid or a base, and if it's strong or weak. This, hopefully you recognize as a strong acid, the most common strong acid, I'd say. So we have that. So the next thing we have to do is actually create a reaction for this. Now we don't have really a reaction happening between two chemicals, we just have a solution of HCl. So that means that HCl is aqueous, and we want to look at how that chemical is breaking down into its ions. So when hydrochloric acid breaks down, we get the hydrogen ion. These are all aqueous because they're all dissolved in water, and we get the chloride ion. So we will be taking a look at how this solution is made and how much product we get from it, how much hydrogen ion, chloride ion we get, and really how that determines our pH of the solution. So at this point we're going to set up an ice table to figure out our amount of hydrogen at equilibrium. I'm going to show you guys how this works for strong acid or base, and we'll look at kind of a shortcut on the next one for this. So we start with our molarity of our solution, and we have a 0.045 molar solution of HCl initially, and we don't have any hydrogen or chloride ion. Now, what's interesting about strong acids and strong bases is that we know that they break down into their ions, and what we can assume at the beginning is that all of this chemical is going to break down, the entire solution. There's very little that will stay together. So what we do is go ahead and subtract the entire amount from our reactant, and we end up with 0 on that side. So using our mole ratio, we know the other side is going to be added, and it's a 1-to-1 ratio with hydrogen, so it's going to be the same number. And it's also a 1-to-1 ratio with chloride ions, so it's going to be the same number. So we can go ahead and find that our amount of hydrogen and chlorine or chloride ion in the solution is the same as what our hydrochloric acid is at the beginning. So basically we're assuming that all of this breaks down into each of the ions. Since everything's a 1-to-1 ratio, we keep that same amount for each chemical, and we can go from there. So this is kind of a easier way when we look at strong acids or strong bases. We can go ahead and assume that the molarity of the solution is the same for a molarity of our ions if they're a 1-to-1 ratio. If it's, say, a 1-to-2 ratio, then we have to double the number still. So that's not awful. Just a little extra step. So from here we can determine our pH using our amount of hydrogen at equilibrium. So we know that there's 0.045 molar solution of hydrogen at equilibrium. So we use our pH equation, negative log of the concentration of hydrogen, and our pH equals, let's do some calculating, negative log 0.045, and we get 1.3467, all these decimal places. We do want to check our significant figures. In our original number we had 2, so we want to have 2 decimal places in our pH value. So 1.3, and we would have one more decimal place, the 4 would round to 5. So our pH is 1.35. So it's a little bit different approach to just calculating pH, where we're just given a value and can plug in. We have to do a little calculating. So we're going to take a look at how this applies to a base reaction. If you're not sure about what I just did, maybe go back and rewatch that part. But I'm going to keep going. You can always rewind. Alright, our next one, we are going to calculate the pH of a 0.90 molar KOH solution. So again, the first thing we want to ask ourselves is this an acid or base? Hopefully you recognize this as a base. And is it strong or weak? This one happens to be one of our strong bases. So go ahead and write that down. Our strong base. So we're going to take a similar approach. We want to go ahead and write out a reaction of this dissolving. We've got an aqueous solution in equilibrium. So we're going to break down into potassium ion and hydroxide ion. We get our reaction. Now, just like above where we assumed that the amount of KOH we were given ends up all breaking down into our ions, we can assume that here. So instead of writing out the entire ice table and taking all that time, we can kind of jump ahead. So we know at equilibrium none of this is going to be left, and it's all going to break down into our potassium and our hydroxide. Since they are 1-to-1 ratio, we keep all the numbers the same. If you were to have something that is, kind of a side note here, not a 1-to-1 ratio. So for instance, something like calcium hydroxide, where you get calcium and 2 hydroxide ions, we would just have, it would be a 1-to-1 ratio here, and then we have to double the number for the hydroxide. So it's just kind of a side note. So from here, we have, we want to find pH, but we don't have a hydrogen ion concentration, but we do have hydroxide. So what we can calculate at this point is POH. So negative log of our concentration of OH, so 0.90. And we can calculate that. So negative log of 0.90. And we get 0.045, so a pretty small number. We have 2 significant figures in our original, so we want 2 in our answer, so 2 decimal places. 0.05, 2 decimal places. And I know that's weird that we're not counting, that we are counting that 0 as significant, but it's just the number of significant figures becomes our number of decimal places to keep in a POH or pH. So now we want to go ahead and find our pH, and we can use our other equation. We know that 14 minus our pOH, so 0.05, can give us our pH, 14 minus 0.05. And our pH is 13.95. So we keep that 2 digits there, 2 significant figures, and that would be our answer. So, the strong acids and strong bases are pretty straightforward. There's not a lot of crazy things that happen with them. Just some things you can kind of have a shortcut and assume that these things break down into just the ratio of their ions and go from there. What does become a little bit more complex is when we have a solution that has a weak acid or base. So it says to calculate the pH, number 3, at 25 degrees Celsius, of a 0.3 molar solution of acetic acid, so we have our acetic acid, and it said it is weak acid responsible for the characteristic odor of acidity and acidity of vinegar. So acetic acid is essentially vinegar. Gives us our Ka value. So if you remember back when we were doing regular ice tables, when we were given a Ka value and we were asked, or a Kc value and we were asked to find it, we probably had to use the variable. Well, we're going to have to do that here. So first thing, we recognize it's a weak acid. We're told that. We know also it's an acid because it says it's a Ka value, which means acid. So from here, we can set up our ice table and our reaction. So we have our acetic acid solution, and that is going to break down into our hydrogen ion, and the one that it gives off is this one hanging off the end, and the acetate ion. Alright, we're going to go ahead and set up our ice table. And plug in our initial values. So we're given 0.30 molar solution of acetic acid and nothing for the other two. So we have no other information we can use to fill in this table. We can't assume that all of it breaks down because it is weak. We know that most of it won't break down. So what we're going to use is X. We're going to say, okay, it's losing some amount of X, some of it's breaking down, we don't know how much. And this side is going to gain some amount, and we'll use X. We still use our mole ratio, so 1 to 1 to 1. And we can set up the rest of it from there. So we get 0.30 minus X, X, and X. So we're kind of used to setting up these ice tables. It's not too bad at this point. And now we're going to follow through like we normally do. We're going to set up our expression. So we're used to Kc or Kp. Well, this one is Ka because it's an acid. So Ka is equal to your concentration of hydrogen and acetate ion over your concentration of acetic acid. I do have a lot of people asking if you include these charges, and you do because you want to represent the correct chemical, and those charges are part of that chemical. So now we're going to plug everything in. Our Ka value that's given is 1.8 times 10 to the negative 5. We have our hydrogen and acetic acid are both X, so we get X squared, X times X. And then we get 0.30 minus X. At this point, normally we would take a square root, but we cannot take the square root of this bottom number, or this bottom value, because it's not squared. So we run into a little problem. But what we can do is kind of an odd little thing. If we look at this value, 0.30 minus X, we know that not much of this is going to actually break down. It's a small concentration or small amount, and the amount of X that's actually going to break apart, those few molecules that do break apart, is going to be so small that once we round our answer to significant figures, so say X was 0.0003, right? It's a very small number. So once we were to round this number to significant figures, it actually wouldn't change the 0.30 at all. So X is so small, or we assume X is so small that our value, 0.30 minus x, is pretty much equal to just 0.30. We drop the x because the x is so small that it's not going to affect our number. So what that allows us to do is rewrite our equation without this x here. So we get 1.8 times 10 to the negative 5. Now it doesn't eliminate all the x's. You can't just drop x and be done. You still have to solve for something. So we only drop that one value, that one x value, and we solve from here. So the first thing we're going to do is multiply the 0.3 to the other side. So we have 1.8 times 10 to the negative 5. And we're going to multiply that by 0.3 and change the sign to rotation. 5.4 times 10 to the negative 6. And that equals x squared. Scooch this down so you can see it. From here, we're going to go ahead and take our square root of both sides so we can get our x value. So x is going to equal the square root of that same number, 2.3 times 10 to the negative third. So that is our excuse me, our x value. Now, of course, as usual, we're not done. We want to state that our hydrogen ion concentration and our acetate ion concentration are both 2.3 times 10 to the negative third molar. I'm going to go ahead and show you guys what that looks like if we were to plug that into here as our x. So up here, I guess. So 0.30 minus our 2.3 times 10 to the negative third. We get a pretty small number. Now if I was to round this to significant figures, I only have 2, so we would have to, 7 would round up our 9, and we would end up with 0.30. So it doesn't actually change this number at all. So our concentration of CH3COOH at equilibrium is still 0.30 molar. So that doesn't change. It's kind of odd, but it isn't. Our goal here was, though, to find our pH. So we have our hydrogen ion concentration. So pH equals the negative log of 2.3 times 10 to the negative third. So we take negative log of that value. We get 2.638. So we want 2 significant figures. That's what we've been keeping. So 2 decimal places, so 2.64. So our answer, pH equals 2.64. So that is our final value. So these are a little bit different. We do need to go ahead and set up our reaction for our weak acid. We set up our initial concentrations, use our x value. The odd part here is assuming that the x on the left side is so small that it's not going to affect our value, and we saw that at the end when I calculated it. And we do our calculations normally. It is good to actually state that you're assuming that your 0.30 minus x is equal to the 0.30, so that it's clear what you're doing and it can be followed. So we've got 2 more examples that we'll take a look at. Our next one, kind of similar. So we want to find our pH of a 0.2 molar solution of HCN, where Ka is 0.9 times 10 to the negative 10th. So it doesn't say if this is an acid or a base, but we should be able to recognize, number 1, it gives us Ka, so that's telling us it's an acid, and it has that hydrogen out front. Now this is not one of our strong acids on our list, so we would say this is a weak acid. So we should recognize that. So what we're going to do is start with our reaction, HCN aqueous, breaking down into hydrogen ion and the cyanide ion, setting up our ice table. We can go ahead and plug in our initial value for each chemical and go from there. So just like we did on the last one, We don't know how much is going away from this side, and we don't know how much is being added on the other side, so we're going to use x values. And we're going to go ahead and set up the rest of our ice table. So this becomes pretty standard. We get very similar ice tables on a lot of acid-base reactions, or acid and base reactions. So from here we want to set up our Ka equation. So Ka is the concentration of our hydrogen ion and our cyanide ion products, both raised to the first power, over our reactant, HCN, hydrogen cyanide, to the first power. And we can plug everything in. 4.9 times 10 to the negative 10th is our Ka value. Hydrogen and cyanide are both x, so we get x squared. And HCN is 0.20 minus x. And again, we can go ahead and assume that our x value is so small that it's going to be, it's not going to affect our outcome here. So we assume that 0.20 minus x is about the same as 0.20. Okay, so we rewrite our equation with that. 4.9 times 10 to the negative 10th is equal to x squared. We keep that x on the top, and we reset this bottom part to just 0.20. We can go ahead and multiply this number to the other side. So 4.9 times 10 to the negative 10th times 0.20, 9.8 times 10 to the negative 11th. Equals x squared. From here, we can go ahead and do our square root of both sides. Find our x value. Find the square root. And let's change the scientific notation. 9.89 times 10 to the negative 6. So we're keeping two sig figs, so 9.9 times 10 to the negative 6 is our x value. There we go. So now we want to go ahead and state that our hydrogen ion concentration and our cyanide ion concentration are equal to our x value, so 9.9 times 10 to the negative 6 molar is our concentrations. Our HCN, we can go ahead and say we've got 0.20 minus 9.9 times 10 to the negative 6, so we get this 0.19999. So if we were to round this to two sig figs, we still get 0.20. Doesn't change our line, so our assumption works. And then we can go ahead and find our pH. So our pH, we use the hydrogen ion concentration, so negative log of 9.9 times 10 to the negative 6th, and we get negative log 9.9 times 10 negative 6, 5.004. So we want two significant figures, so we have two decimal places, so 5.00 is our pH. So this process becomes kind of quick after a while. Your ice tables are going to look very similar each time. We're going to make that assumption about our x value on the bottom so we can actually calculate our answer and not use a quadratic formula because no one wants that. And then we can calculate our pH. Got one more example dealing with another base. It's kind of a slightly different reaction in this one. So in this question, it wants us to calculate POH and pH. So we need a hydroxide and a hydrogen ion of a 0.0062 molar solution of NH3 ammonia, where Kb is 1.8 times 10 to the negative 5th. So Kb is our base, our constant for our base. Ammonia is a very common weak base that we should start recognizing here. So in this one, if we were to write our NH3, it's a base. It wants to gain that hydrogen. It's not just a base where it can break down into its two ions. We want to show that hydrogen ion that it is gaining. So the only place we're going to get that hydrogen ion from is water. Oh, water is not aqueous. Water is a liquid. So because water is a liquid, it's going to make our ice table not that bad. So water is going to give a hydrogen ion to ammonia and give us ammonium ion. And we're going to be left with one less hydrogen on this, so we get hydroxide ion. Going off my paper. Alright. There we go. So we set up our ice table. We've got our initial concentration of ammonia, 0.0062. We have no products. And we can go ahead and ignore that water completely. It's there to react, but it's not going to affect our equilibrium because it is a liquid. So from here, similar process. We don't know how much is going away, so we have minus x. We add x to the other side. 0.0062 minus x, x, and x. From here, this time we're going to set up a Kb expression because it is for a base. So we've got concentration of NH4 plus and of OH minus over the NH3. And we're going to plug in our values. So 1.8 times 10 to the negative fifth equals, switching over here, equals our NH4 plus and our hydroxide. So we have x and x squared on the top. I'm going to go ahead and put in our assumption right now. So we're going to assume that 0.0062 minus x is about equal to 0.0062. Go ahead and keep that assumption, and we'll go ahead and just put in the 0.0062 down here. We'll multiply it to the other side. 0.8 times 10 to the negative fifth times 0.0062. Very small number. 1.116. So 1.1 times 10 to the negative 7 equals our x squared. And we can go ahead and do our square root of both sides. Find that x equals 3.3 times 10 to the negative 4. Get our x value. So again, we want to find, we look at our reaction, we have that hydroxide ion here. So what we'll be able to calculate, we have our concentration of hydroxide is equal to x. So we can say that our POH is the negative log of that value. So we get negative log of 3.3 times 10 to the negative 4. And we get our POH is 3.48. Alright, our last step is to calculate the pH from our POH. So we do 14 minus 3.48. And we get 10.52. And that is our POH and our pH values for this. So that's our answered our question. We wanted both of those values, so we have our POH and our pH value. So this one's very similar. We just had to set up our reaction with water so we could get our hydrogen transferring to our ammonia, but water ends up being ignored anyway. Alright, that is the end of our notes. Thank you.